On the night of October 25th, 1944, in the black waters off Samar in the Philippines, a Japanese surface fleet stumbled onto a group of American escort carriers so small and so lightly armed that their crews initially assumed the warships appearing on the horizon were friendly. They were not. What followed was one of the most desperate naval engagements in American history. A handful of destroyer escorts charging battleships with torpedoes to buy time for the carriers to run. The Americans survived, barely, through suicidal courage and Japanese confusion.
What the Japanese commanders did not know, and what their superiors in Tokyo had known for months and chosen not to accept, was that every significant American surface ship in that engagement was reading them. Radar scopes in American combat information centers were painting the Japanese formation in amber light before a single Japanese lookout had raised his binoculars. The Americans knew the range. They knew the bearing. They knew to within a few hundred yards where every Japanese shell was going to fall before the Japanese gun crews had finished loading.
Japan had radar too. By the fall of 1944, Japanese destroyers, cruisers, and battleships carried sets with names like the Type 22 and the Type 13. On paper, the specifications were not embarrassing. In practice, they were nearly useless. American veterans who captured and examined Japanese radar equipment after the war were consistently baffled, not by the sophistication of the design, which was sometimes genuinely clever, but by the quality of the components inside. Resistors that should have been identical were not. Capacitors that should have held a precise tolerance drifted wildly. Vacuum tubes that American factories turned out by the tens of millions, each one tested and gauged and certified before it left the building, were in Japanese sets hand-selected by technicians who rejected 4 out of every 5 that came off the line. The Japanese could not copy American radar manufacturing. Understanding why requires going back not to 1941, not to the 1930s, but to a decision made in a German university town in 1905, and to a single word that the Japanese engineering establishment had never been forced to confront in the way that American industry had spent a century and a half learning to answer. That word was tolerance. The inheritance Japan never received. In the summer of 1905, a young Japanese engineer named Yoshida Bunzaburo returned from 3 years of study in Germany with notebooks full of observations about German manufacturing methods. He wrote admiringly of the Facharbeiter, the master craftsman, who sat at the center of every serious German workshop. A German machinist in 1905 did not simply cut a part to a specification. He finished it. He measured it with a micrometer, compared it to the drawing, and then took a file to the surfaces that needed adjusting until the part fit exactly as it should. The craft was in the fitting. The skill was inseparable from the product. Yoshida brought this model home. Japan, which had opened itself to Western industrial methods only 40 years earlier in the aftermath of the Meiji Restoration, absorbed German craft culture enthusiastically. It fit something already present in Japanese workshop tradition, the ideal of the artisan who took personal responsibility for the perfection of his product, who would not release work that did not meet his own exacting standard. Ceramicists, swordsmiths, lacquer workers, weavers, Japanese craft culture ran deep, and the German model of the Facharbeiter felt less like a foreign import than a validation. What Japan did not receive, because Germany had not fully received it either, was the other half of the story, the American half. 44 years before Yoshida's notebooks, in the summer of 1851, the British committee that visited the Crystal Palace exhibition in London had seen something in the American exhibits that they called, with a mixture of admiration and unease, the American system of manufacturers.
The phrase referred specifically to the interchangeability of parts, to the fact that a rifle built in Springfield, Massachusetts, could have its lock plate replaced with a lock plate from any other rifle built in the same factory, without filing, without fitting, without the intervention of a craftsman's skill. The part dropped in. It was correct before it arrived, because it had been cut and gauged and tested and certified before it left the shop. And the shop's gauges were themselves certified against master standards kept under glass in a federal vault. This system had not come easily or quickly. It had been built over 50 years of disciplined, painful, sometimes humiliating institutional learning at the federal armories of Springfield and Harper's Ferry. It had required the invention of entirely new machine tools, new gauging instruments, new methods of shop management, and a new philosophy of rejection. The idea that a part that did not pass the gauge was not adjusted and shipped, but thrown out, and that the supplier who made it was warned and then dropped and then replaced.
The Americans had also learned something that the Germans and the Japanese had not, that standardization was not the enemy of quality. It was the only reliable path to quality at scale. A German craftsman filing a part to fit could produce a beautiful result for one weapon. He could not produce it for 100,000 weapons. The American gauge, calibrated to 10,000ths of an inch, could. And when the gauge said the part was good, it was good. Not approximately good, not good enough for government work good, but good in a way that could be reproduced identically on a Monday morning in January and a Friday afternoon in August, by a man who had been on the line for 30 years and by a woman who had started 3 weeks ago after her husband shipped out to the Pacific.
Japan's industry, by the time it began producing radar equipment in the late 1930s, had never been forced to learn this lesson. Its Navy was excellent at building large, complex weapon systems, battleships, fleet carriers, long-range torpedoes, through the application of extraordinary craft skill and immense institutional pride. But those systems were made in small numbers, at great cost, by men who were themselves irreplaceable. Japan could build a superb battleship. Japan could not build 10,000 identical vacuum tubes. And radar, above all else, was a game of vacuum tubes. The tube problem. In December of 1941, the United States was not the world leader in radar technology. Britain was. The cavity magnetron, invented at Birmingham in 1940 by John Randall and Harry Boot, was the most significant electronic component of the war. A device that could generate microwave frequency radio waves at power levels sufficient to detect a submarine periscope at useful range, or paint a ground target clearly enough for a bomber to hit it through cloud cover. The British brought the magnetron to America in September of 1940 in a black box carried across the Atlantic by a physicist named Henry Tizard. American engineers at MIT and Bell Labs stared at it and then set about doing what American industry did, manufacturing it. The MIT Radiation Laboratory, established in November of 1940, grew within 4 years to a staff of nearly 4,000 people, and produced, according to its official history, radar and radar-related equipment valued at more than $1.5 billion. The laboratory invented new systems, but the systems were only as good as the components that went into them, and the components were only as good as the factories that made them. This is where the American manufacturing inheritance, the one that ran from John Hall's breech-loading rifle through Eli Whitney's cotton gin to Henry Ford's moving assembly line, became decisive. Western Electric, the manufacturing arm of Bell Telephone, had been building electronic components to standardized tolerances for decades before the war began. Its engineers understood, in a way that Japanese manufacturers did not, that a vacuum tube was not merely a glass envelope containing some wires. It was a precision instrument in which the spacing between the grid and the cathode, measured in thousandths of an inch, determined whether the tube amplified correctly or not at all. Those dimensions had to be held to specification not once or twice, but millions of times, by workers who might never have heard of electron physics, on assembly lines that ran 24 hours a day, 7 days a week, for years.
Western Electric built gauges. It built jigs and fixtures that held components in precise relationship while they were welded or crimped. It built testing equipment that evaluated every completed tube before it was boxed. Not a sample, not a batch, but every single one. A tube that failed the test was thrown out. The supplier was put on notice. The tolerance was not relaxed to accommodate what the production line could deliver. The production line was rebuilt until it could deliver what the tolerance demanded. By 1944, American factories were producing vacuum tubes at a rate of approximately 100 million units per year. The rejection rate at final test was under 2%. In Japan, at the same moment, the Navy's primary supplier of radar tubes was producing approximately 400,000 units per year. The rejection rate at incoming inspection, meaning tubes that had already passed the supplier's own internal tests, was running between 30 and 60%. This was not a secret. Japanese naval engineers knew it. They wrote reports about it. A 1943 memorandum from the Navy Technical Department, declassified after the war and translated by American occupation authorities, stated the problem with painful clarity. The component manufacturers are not holding dimensions. Each factory is interpreting the drawings differently. The result is that tubes of nominally identical specification cannot be interchanged between sets without individual adjustment and testing. Individual adjustment and testing. The German Facharbeiter in a different uniform. The same problem in a different ocean, in a different war, with the same consequence. The man who should have been Japan's Knudsen. In January of 1942, a Japanese industrialist named Aikawa Yoshisuke submitted a memorandum to the Cabinet Planning Board in Tokyo. Aikawa had built Nissan from a small holding company into one of Japan's largest industrial conglomerates, and he had done it partly by studying American manufacturing methods more carefully than almost any of his contemporaries. His memorandum argued, in terms that were respectful but unambiguous, that Japan was about to lose a production war it had voluntarily entered against an opponent it could not outproduce. The core of his argument was not about raw materials, though he discussed those. It was not about labor, though he mentioned that too. It was about what he called Seido Kanri, tolerance management. He wrote that Japanese manufacturers were producing components whose dimensions varied enough between shops and sometimes within the same shop that final assembly was requiring extensive hand fitting that could not be accelerated. He argued that until Japan established a central system of standardized gauging, certified against national standards, enforced by government inspection at every tier of the supply chain, its production rates would never approach what its raw material inputs should theoretically support. Aikawa was thanked for his memorandum. He was not given authority to act on it. The Cabinet Planning Board was preoccupied with steel allocations and oil reserves and the question of how long the Southern Resource Zone could supply the home islands. Tolerance management was an engineering problem. It would be handled by the engineers. The engineers handled it by working harder. They hired more skilled workers. They increased inspection staffs. They sent teams from the Navy Technical Department to visit suppliers and identify the worst offenders.
individual factories improved. The system as a whole did not change, because changing the system would have required exactly the kind of central authority that Aikawa had requested and been denied. An authority analogous to what William Knudsen had exercised in the United States, walking into factories and confiscating hammers and files, and telling suppliers that parts that failed the gauge would not be paid for, period, regardless of how many shifts the factory had run to produce them.
Knudsen had that authority because Roosevelt had given it to him, and Roosevelt had given it to him because American industrial culture, however imperfectly, understood that standardization was a form of discipline that had to be imposed from outside the individual workshop. No shop superintendent wanted to throw out parts that his workers had spent time making. The discipline had to come from above, from gauges that answered to standards, that answered to a central authority that was not interested in excuses. In Japan, that authority never materialized. The Navy and the Army ran competing procurement systems that used different standards. Suppliers who served both branches built components that fit neither specification precisely, but that both inspection services could be persuaded or encouraged to accept. The result was a radar ecosystem in which every set was essentially custom built, in which field maintenance required technicians who could improvise, and in which a tube that failed in combat could not reliably be replaced by pulling one from the supply box. What American radar did to the Pacific War. By the middle of 1943, the consequences of this divergence were becoming visible in ways that Japanese commanders could not explain within their existing frameworks of understanding. At the Battle of Empress Augusta Bay in November of 1943, an American cruiser-destroyer force encountered a Japanese force in darkness and rain. The Americans opened fire while the Japanese were still maneuvering to identify the contacts on their own inferior radar screens. 3 Japanese ships were sunk. The Americans lost none. The Japanese commander filed a report attributing the outcome to American torpedo fire of unusual accuracy. He did not have a conceptual framework that allowed him to understand that the Americans had seen him in the dark. At the Battle of the Philippine Sea in June of 1944, American radar-directed fighter control destroyed approximately 300 Japanese aircraft in 2 days of fighting, at a cost of around 30 American planes. The engagement was so one-sided that American pilots called it the Great Marianas Turkey Shoot. The Japanese pilots were not, on the whole, less brave. Some of them were less experienced, but many of the men flying that day were veterans of Pearl Harbor and Midway. What they encountered was an air defense system that could see them coming from 150 miles away, calculate their approach vectors, and put American fighters in position to intercept before the Japanese formations had reached their launch points. The radar that made this possible, the long-range search sets, the height-finding sets, the fighter direction systems, depended on vacuum tubes that worked every time, on components that held their calibration in the heat and humidity of a Pacific carrier deck, on spare parts that could be pulled from a standardized supply system and installed by a technician who had been trained to follow a procedure, not to improvise. Japanese radar operators, watching their own screens, saw something else. They saw displays that flickered and drifted as tubes aged unevenly. They saw ranges that had to be constantly recalibrated because the components did not hold their initial settings. They saw, in the worst cases, screens that went dark entirely during an engagement because a tube had failed and the replacement pulled from the spares bin performed differently enough that the set required full retuning before it could be used. A 1944 report by the American Naval Technical Mission in the Pacific, based on examination of captured Japanese equipment,
noted that Japanese radar sets showed evidence of extensive field modification. Resistors had been substituted with non-standard values. Capacitors had been replaced with units of similar but not identical specification. Filter circuits had been bypassed entirely. The technicians who had made these modifications were clearly skilled. They had kept the sets running when the proper parts were unavailable. But each modification pushed the set further from its design specification, degraded its performance, and made it less interchangeable with the set on the next ship. The American analyst writing the report used a phrase that would have been familiar to any student of the Springfield Armory. The sets had been hand-fitted to keep them operational. They were no longer a system. They were a collection of individual solutions.
The culture that could not change in time. In the spring of 1944, with the strategic situation deteriorating across the Pacific, the Japanese Navy's Bureau of Aeronautics commissioned an internal study of electronic component quality. The study was completed in July, 3 weeks after the Marianas defeat, and its conclusions were not distributed beyond a small circle of senior technical officials. The study found that the fundamental problem was not the design of Japanese radar systems, which it rated as adequate. It was not the expertise of Japanese engineers, whom it praised as capable and dedicated. It was, in language that must have been difficult to write and more difficult to read, the manufacturing culture of Japanese industry itself.
The study's authors had examined American technical literature captured in the Philippines and translated by Navy intelligence. They had found descriptions of the American gauge tradition, the system of certified master gauges, working gauges, inspection gauges, and go-no-go fixtures that governed production at American electronics factories. They had found references to the American Standard for Electronic Components, a military specification system called MIL-SPEC, which defined not just the electrical performance of a component, but its physical dimensions, its environmental resistance, its testing procedure, and its acceptable failure rate.
Nothing equivalent existed in Japan. The study recommended the immediate establishment of a central gauging authority, the development of national standards for electronic components, and the assignment of Navy inspectors to every tier of the supply chain with authority to reject non-conforming lots without appeal. The recommendations were sound. They were also, by July of 1944, approximately a decade too late. Building a gauging tradition of the American type had taken the Springfield Armory 20 years under John Hall, working without interruption, with government backing, in peacetime. Japan was fighting a two-ocean war, absorbing B-29 raids on its home islands, losing ships faster than its yards could replace them, and watching its fuel reserves fall towards zero. Changing the manufacturing culture of an entire industrial economy in this environment was not a planning problem. It was not a resource problem. It was simply impossible. The knowledge could be written down. The authority could be delegated. The gauges could, in theory, be built. But the 10,000 daily decisions made by 10,000 supervisors in 10,000 workshops, the decisions about whether this part was close enough, whether this tube was acceptable, whether this dimension was within tolerance or needed one more pass with the file, those decisions came from a culture that had been forming for 40 years. And a culture does not change because a bureau in Tokyo issues a memorandum.
American industry had not changed its culture by memorandum either. It had changed it over a century and a half through competitive pressure and government contracts and the slow, grinding accumulation of institutional learning, through men like John Hall, who spent 20 years developing a method that worked, and men like William Knutson, who enforced that method with the authority of a wartime production chief. Japan had none of that inheritance, and no time to build it.
The last sets.
In the final months of the Pacific War, as American forces moved through the Philippines and toward the Japanese home islands, captured Japanese radar installations were examined with increasing thoroughness by American technical teams. What they found told a consistent story. At a shore installation on Luzon, they found a Type 13 air search radar, a set that Japanese engineers had designed specifically to detect low-flying aircraft, a genuine response to the tactical problem of American carrier strikes. The design was competent. The installation showed evidence of careful, skilled work. But when the American technicians measured the components against the set's own technical manual, they found variations that would have caused the set to fail incoming inspection at any American military electronics facility. Tubes that should have been interchangeable with the spare units in the adjacent storage room performed differently enough that the installation's logbook showed 17 separate recalibration events in the preceding 90 days. 17 recalibrations in 3 months, each one requiring a skilled technician, each one pulling that technician away from maintenance work on other equipment, each one introducing its own small accumulated drift from the design specification.
At Okinawa, American signals intelligence teams monitoring Japanese communications in the weeks before the invasion detected something that initially puzzled their analysts. Japanese radar stations were going off the air not in response to American jamming or American attack, but apparently spontaneously, for periods of 1 to 4 hours, in the middle of their operational duty cycles. The pattern was consistent across multiple stations. The analysts eventually concluded, on the basis of subsequent technical examination, that the stations were going dark for emergency tube replacement and the recalibration that followed. The operational readiness rate of Japanese radar in the Okinawa campaign was later estimated at approximately 40%, meaning that at any given moment, roughly 3 of every 5 Japanese radar stations in the theater were either off-air or performing below their design specification.
American radar readiness in the same campaign ran above 90%. When it failed, replacement parts from standardized supply, pulled from wooden crates stenciled with part numbers, dropped in without adjustment. The technician did not need his caliper. He did not need his file. He bolted it down, and it worked.
The answer Japan could not give. After the war ended, in the late summer of 1945, teams of American scientists and engineers fanned out across the Japanese home islands to examine the technical and industrial infrastructure of the defeated enemy. The reports they filed were extensive, and many were complimentary about Japanese engineering capability. The designers of the Zero fighter were acknowledged as genuinely innovative. The Long Lance torpedo was described accurately as the finest weapon of its type in the world. The engineers who had built Japan's optical instruments, its mechanical computers, its submarine detection equipment, were credited with skill and creativity. But the reports returned repeatedly to the same fundamental observation. Japanese industry, in almost every sector examined, was producing components whose dimensional variation was too large to support the interchangeability that modern weapon systems required. The optical instruments were excellent, but could not be repaired in the field because the replacement lenses had to be individually fitted. The mechanical computers were accurate, but broke down at rates far higher than equivalent American devices because their gear trains were hand-fitted rather than gauge-made. The submarine detection equipment was, in concept, adequate, but its performance in service bore little relation to its design performance because the components degraded unevenly and could not be replaced from standard stock. One American engineer, writing in the summary report of the naval technical mission to Japan, used language that echoed, almost exactly, what a German engineer had written about the Type 21 U-boat program. He wrote that Japanese electronics manufacturing had never fully made the transition from craft production to system production. The craftsmen were excellent.
The systems failed.
Across the Pacific, in the shipyards and factories that had built the instruments of American victory, a different story was being written in the ledgers and the tooling records and the gauge calibration logs. 49,000 Sherman tanks, 80,000 aircraft in a single year, 2,700 Liberty ships, 100 million vacuum tubes, 98 of every 100 of them passing final test. The Japanese Zero, on paper, was the finest fighter in the Pacific in December of 1941. The Japanese Long Lance torpedo was the finest torpedo in the war. Japanese optical sights were among the best in the world. Japanese naval architects could design a ship that made American designers envious. None of it mattered in the end, because a torpedo that cannot be replaced when it is expended is a torpedo that can only be fired once. A radar that requires a skilled technician to recalibrate every 6 days is a radar that goes dark when the skilled technicians are dead. A fighter that cannot be produced at the rate of its losses is a fighter that disappears from the sky. What mattered was whether the part dropped in or had to be fitted. America had been answering that question since 1819. Japan, for all the brilliance of its engineers and the courage of its soldiers, never answered it at all. This account draws on technical reports from the Naval Technical Mission to Japan, 1945, the MIT Radiation Laboratory series, David Hounshell's From the American System to Mass Production, post-war analysis of Japanese radar programs by the U.S. Strategic Bombing Survey, and the records of the Joint Army-Navy Committee on Electronic Standards.